This lesson is about some of the graphs that you might see of binomial distributions. So if we graph the probability of each of the number of outcomes, so for example, if I'm flipping 5 coins, probability of getting no heads is quite small. Probability of getting all heads is quite small, but getting 2 or 3 is quite likely. So the shape of this distribution looks sort of like a big triangle. And thing to note is that it's symmetrical. So either side of this line, we've got some symmetry. If we increased our number of trials to say 15, we'll see the same thing, that it's really unlikely to get either 0 or 15 heads, and quite likely to get 7 or 8. So we can see it's starting to take this sort of a bell-shaped curve. If we increase it again to 25, it's almost impossible to get no heads, almost impossible to get all heads. More than likely, it'll be happening around the 12 or 13, or really from 9 to 16 or 17. And we can see it really starting to make that sort of a bell-shaped curve. So things to note: when the probability of success is 0.5, the graph is symmetrical, and as the number of trials increases, the curve becomes smoother. So there's a video that you can watch that demonstrates this, where we're feeding Skittles into this Galton board machine, and as we feed more and more Skittles in, there's half a chance of it going either way. We start to get this this bell curve shape. Okay, so you can have a look at that video if you want, or type in Galton board into uni for some more interesting ones of these. Okay, so symmetrical when probability of success is 0.5. If the probability of success is not 0.5, then we start to get a bit of skewing. Okay, so with 8 trials, if the probability of flipping a head was actually 0.2, if we had the coin weighted in some way, we would see that it's more likely to be around the lower end, okay, and less likely for us to get, say, 4 or 5 heads. I would say this is positively skewed. So in every scenario where probability of success is less than 0.5, it means it's positively skewed or skewed to the right. So you can think of this as, where's the most frequent value? The direction the tail goes is the direction of the skew. So it's in the positive direction, okay, or in the direction to the right. We already know at 0.5, we've got that symmetrical normal distribution, bell curve. We'll use those words a lot this term. And if the probability of success is greater than 0.5, then it's more likely that we'll get a lot more successes. And it's said that it's negatively skewed. So from that average value, skewed to the negative direction or to the left. So for you to confirm your understanding of the skew, you can have a go at those 3 problems. The second part of this lesson is to look at some problem solving involving binomial probability formulae. So just a few tips: ensure you state any assumptions as you go. Ensure you understand what the question's asking you to find, and write down any known facts. Formulae, values of parts of the formulae, everything you can. So have a go at this first problem. Maybe you want to have a go by yourself first, so press pause and have a crack. A basketball player wants to impress their friends by shooting 10 three-point shots in a row. He believes the probability that he can achieve this feat is 0.9. What is his probability? What is his probability of success? So probability of landing each individual shot successfully if his belief is true. Is his belief reasonable? So let's see what we go here. So I'm going to make an assumption here. I'm going to assume it's a binomial probability distribution. Okay. Specifically, assume that P doesn't change. Okay, meaning he's taking 10 shots. his probability of success isn't going to change through the whole experiment. He's not going to get tired, not going to get nervous as he takes more shots, or more comfortable as he takes more shots. So that assumption's pretty key. What things do I know? I know there are 10 trials, because he's shooting 10 3-point shots in a row, and he believes his probability of having 10 successes in those trials is 0.9. What's my task? I'm trying to find P. So I'll write down the formulae, see what I can do. So I remember my formula, NCX, P to the X, Q to the N minus X, and I'll substitute in all the values I know. So I'm really interested in the probability of him having 10 successes from 10 trials. So P to the power 10 and Q to the power 10 minus 10. Okay, this will be interesting. Do I know anything? Yep, I know that probability on the left hand side is actually 0.9. 10C10, I could probably figure out what that is. NC10 is 1 times P to the power 10 times Q to the power 0. So 0.9, 1 times, don't need to write that, P to the power 10 times Q to the power 0. Anything to the power 0 is 1, so it's times by 0 again. I just need to now take the 10th root of 0.9, which will tell me what his probability of each individual shot will be. So the 10th root of 0.9 is 0.9895. So his probability of success in each basket throw is 0.9895. So that's what the p-value needs to be. Is his belief reasonable? Well, I'd probably say that that's not reasonable. I don't think there's anyone who can shoot 98.95% of 3-point shots. Not even the professional basketball players. So I don't believe it's reasonable, as it's too high for this sort of experiment. So his belief is not reasonable. He's basically dreaming that 9 times out of 10 he'll be able to shoot 10 buckets in a row. Our final problem to have a look at, the Mars bar promotion, is that 1 in every 6 bars is a winner. There's a chocoholic obsessed with winning and wants to know how many bars he needs to buy so that his probability of winning at least once is above 99%. All right, let's have a look at this. So I'm going to define success as winning a bar. So my probability of success is 1 on 6. Probability of failure is 5 on 6. How many bars does he need to buy? So the number of bars, I don't know. But he wants his probability of getting at least 1 bar to be greater than or equal to 0.99. So that's all the information I have. Do I know anything about this? Made any assumptions? Okay, so assume from random batches. So P doesn't change. So again, I'm assuming that it's a binomial distribution. Write down my formula, see what I can do with it. Okay, so I'm interested in the probability of getting at least 1. So another way I can write probability of at least 1 is all the probabilities except getting nothing. Okay, so I'm going to try and solve for essentially for this. with 0.99 in the left hand side. Okay, so I'm attempting to solve this. I want to know, to get 0.99, what does my n value need to be? So after 0.99 here, 1 minus, well, I'll put this formula in now. So 1 minus, when lowercase x equals 0, I'm doing n trials, so n C0, probability of success is 1 on 6, and probability of failure is 5 on 6. I'm trying to find what that n value needs to be. NC0, if I don't know anything about permutations and combinations, I could try 5C0 or 9C0, see if there's any pattern to the results. 15C0. So regardless of what that top number is, NC0 is always going to be 1. So this here will always be 1 times something to the power of 0 is 1 times 5 on 6 to the power n. Okay, so what I'm ending up solving is going to be just a exponential equation. So I can do a little bit of rearranging. I'll bring the 5 on 6 to the power n to this side and the 0.99 to the other side. Okay, and you should be okay solving these now. I'll get log base 5 on 6, okay, of 0.01. Whatever this works out to be. N value of 25.29 bars. And so I conclude should need to buy 26 bars to guarantee a winner, which is a lot of chocolate. Okay, so that's based on the assumption that it's binomial probability. Okay, if it was the case that it wasn't binomial, okay, then I couldn't do this calculation. Ask for the effect of your assumption. Okay, we'll always write something like this, that if it's not true, the prediction that we made wouldn't be valid. It's a little bit of problem solving. Here's a lot more for you to practice.